started. So first, a quick show of hands. Who in here doesn't make mistakes? I don't, so right there. All right, well, congratulations. You can just leave then. All right, today's what we're going to talk about today will have no impression on you whatsoever. Of course, I did grade your midterms, so there's a little disconnection there, but that's okay. Let's just assume that was just a fluke, all right? Okay. So, what we're going to talk about today is testing. I don't know how you guys feel about testing. Do you guys do testing now? Yeah, big time. Yeah. We may not call it testing, we may just call it like fixing what's wrong. Have you guys had the first electrical engineering lab?
Yeah.
Yeah. All right. Welcome to the oscilloscope, and here's how you use it, and all that sort of stuff like that. All right. So you've already had a little bit of a taste of it, at least of some sort. What's interesting is when you get out in the real world, there's a real good chance that your job's going to be a testing job. I mean, we all like to think about ourselves as being, God's gift to design and stuff like that. But the reality of the situation is, in the world of electrical engineering, there's far more testers than there are designers, right? I can design things once, but I have to test it over and over again. And it takes smart, bright people who are actually very good at doing testing to be able to do that. So, what we talk about today is actually chock full of vocabulary terms that you might want to jot down and remember, because during, job interviews, this is exactly the vocabulary you're going to hear people talking to you about. Because they're going to be talking to you about basically the whole design process. And testing, no matter how you feel about testing, is a huge part of it. Because if you're creating a product or if you're designing something, you can't release it unless it works. Because otherwise guys in really nice suits show up and say, hi, we're from the legal firm of we sue them and take your money, and we're here to basically take all your money, right? So testing is a huge, huge thing, although we may not talk about it all that much. So let's take a little step back in time. A while ago, we talked about engineering requirements. Remember that? On the midterm? Yeah, there was actually 4 components to engineering requirements. Do you all remember what those 4 components were? First off, they are, if you're writing a good engineering requirement, what's the very first thing? It's supposed to be abstract. Okay, that's cool. That's all good. Gold star. Right. So the requirement should specify what the system will do. And of course the key thing there was not how it's going to do. That's cool. What was the second one? Do we remember?
Unambiguous.
Unambiguous. Very good. Exactly. Each requirement should have a single unambiguous meaning. It should be stated in short, complete sentences. So that's sort of an interesting thing there. What we're going to start to discover is the reason we're keeping them short is that if it's nice and it's a short one, then you can test that requirement, right? I can create a test case or a test set for that particular requirement. If you're going on for a paragraph of the requirement, then all of a sudden that testing is going to be a lot trickier. What's the third one? You guys remember? Traceable. Very good. Excellent. So we should be able to go from actually design back to the requirements, and we should be able to go from the requirements back to the user, right? There should be a reason that we have this engineering requirement. Not just, I really like a super high-res display, so we decided to add a super high-res display. There should actually be really a customer requirement for it, but you shouldn't be implementing it anyway. Do we remember what the 4th one was?
Verifiable.
That's probably the big payoff for today. Congratulations, verifiable. You gotta be, having a requirement is great, but if you're not going to be able to confirm that you actually worked that requirement into the design, it's not going to be any good. If you've buried it so far in that it's not able to be tested, well, that's not going to do any good. So, there you go. You have done it. You have created a design. You can hold it in your hands. You look at it. You realize that now the world is going to be a better place because you designed it, you created it, and here it is. So what do you do now?
Sell it.
No. You plug it in.
Very good.
You plug it in. You don't know if it's going to work. You plug it in. And when you plug it in, what happens?
It shorts out.
Or even worse, potentially nothing. All those lights that were supposed to flicker on, or all of whatever was supposed to, nothing happens. And at this point in time, what do? You fall to the floor, and kicking your legs, you go in a circle while sucking on your thumb. Well, okay, well that's one thing. That's entirely
Great.
You pack it up, get the little cardboard box, and walk out of there. Hey, didn't work out. It was a good try. You got to do something. So what do?
Fix it.
Fix it. How are you going to fix it? What's wrong with it?
Test engineers.
You got to do something right. Because if it looks like this, you've got an issue. And perhaps you shouldn't have plugged it in the first place. Yeah, it happens to all of us, actually. All right. So lots of systems undergo testing during their development. So an interesting question is, when do we do testing? Do we get it all done and then start doing some testing? Woohoo! No, when should you do testing? As you go along, right? Y'all going to be working on some capstone projects at some point in the future? You're going to get the whole capstone thing done and then plug it in? Woo! Oh, God. There's not enough time in the semester for you to fix that particular issue that went on, right? So really, testing isn't a big module that you do after you get done with the design. It's all sort of worked in together, right? So you do a little bit, you test a little bit, you do a little bit more, test a little bit more. It's almost like the agile design method, right? Where we talk about design, test, stuff like that. Systems need to be tested in order to ensure that they meet their requirements, right? That's the whole reason that we're doing this. Okay, and what was one of the requirements of an engineering requirement? It had to be verifiable, right? Okay. Now, we always say, we're going to sneeze. When do you want to catch an error? Early in the process or later in the process?
Early.
Why?
Because it's preventable.
It's preventable. Well, yeah, that's true. And I'm sorry, it's cheaper? Why? I mean, I've heard that, but...
When errors compound on top of each other, it just takes more time to troubleshoot.
Well, that's a good point. And I guess as you continue to add to your design, there's more layers, right? So if something's going wrong, the question is, where is it, right? So it will take you longer to find it, the longer in the process, right? And if it's mucked up, and you built stuff on top of it that's also mucked up, then to fix it, you may also have to fix additional layers, right? So the longer an error exists in your design, the more costly it's going to be for you, for the company, for everybody like that. So the earlier you can find it, the better. So how are you going to be finding it? You're going to be doing what? Testing. All the way along, right? You're not just waiting until the end, you're doing it all along. All right? We're going to be talking about fundamental testing concepts and how they can be applied throughout the lifetime. So let's think about this. So we've been spending our time talking about this stuff. So we talked about those requirement specifications. Oh, we talked about system design. We assume that there's a construct phase where you get wires and stuff and batteries and you all hook it all together. And now we flip the switch and nothing happened. So we find ourselves in the debugging phase. That's cool. It turns out in the world of testing, and there is a world of testing, there are people who do nothing but testing. Okay? There's an equivalent functionality for each one of the things that we did over there. So let's take a look up here. Acceptance test. What's interesting is you can build an acceptance test when you're building your requirements specification. So, we're coming up with this grand requirements document that has two types of requirements. What are the two types of requirements? Marketing, engineering. Exactly. Great. So we have this document. This is what this blue widget thing that we're working on should do, right? Fantastic. Well, once you have that, you can write an acceptance test, right? So if I was creating a Blu-ray DVD player, right? I mean, one of the requirements would be I should be able to put in a Blu-ray DVD and I should see a picture on the screen, right? Man, you write a requirement specification, I can write your acceptance test right off the bat. If my fancy Blu-ray DVD player should be able to play Netflix movies, stream it over the internet, poof, I can put that in my acceptance test. Day one, once you've written that requirements test, I can create an acceptance test. When I was working for Boeing, we had massive acceptance tests. I mean, huge. What it was page after page of tests that the Navy personnel would sit right next to us. We would execute the test. They would see that it had executed correctly, and then they would sign off on the bottom of the page, page after page after page. And the reason we did it this way is because the Navy could afford to pay for it. Somebody to sit there and go through the testing test. So they had an extensive acceptance testing program. Basically, if we gave it to them, it did exactly what they had contracted to do. Integration test, of course. When you're doing your system design, you want to be thinking about the test. See, this is sort of the difference between a novice or a green engineering designer. You go, wow, how am I going to do my design? Oh, it's going to be the coolest design. It's going to have these inputs, and it's going to do this functionality, and it's going to produce these outputs. The more seasoned or the more mature one says, listen, okay, I've got inputs, I've got outputs, I've got functionality. How am I going to test this? So as they're creating their design, they're thinking, I need to be able to test this. Do I put in test points? Do I have to put in additional output values? How am I going to make this easy to test? Because I know when I flip the switch, it's not going to work. Okay? So I want to make that testing period as short as possible. So you want to be thinking about your integration test while you're doing your design. When you're actually constructing it, now you can talk about something called unit tests, which is the lowest level of testing. It's where we, this input does this and produces this output. Does that actually happen? You're going to want to be thinking about that while you're actually doing the construction of it. And of course, when you're doing debugging, you use all of these.
So you should be testing it along the way, right? Each component versus the whole system itself.
That's exactly correct. So if you were building a car, for example, great. You start out with what, maybe 4 tires? Okay, and then you've got an engine. You want to test to make sure that the engine worked and that it spun stuff, right? And produced electrical power. If the engine's working fine, then you could hook up the spinning part to maybe the front wheels. Make sure the front wheels go. Oh, look, they do. Then you could hook up the spinning part to the back part. And all 4 wheels. Cool, now you've got a lot of stuff working. Now you can worry about air conditioner and stereo and stuff like that, because you got the basics working. If you put the whole thing together, turned it on, and the windshield wipers went, and the shot CDs out, and the tires didn't do it all, you've got yourself a heck of a debugging task ahead.
When that happens.
Man, that's just a bummer when that is. Does this all make sense? So let's see, testing begins when construction, so the system starts, testing process works. Here's the interesting thing. Testing process works in the reverse direction. So we start with the most detailed. So you've constructed it. Now we start working at the most detailed. We're down in it. Let's test A to B, A to C. Then we move up into the higher levels as we go along. Testing usually starts with the low-level debugging of the components as they're developed, followed by unit testing of the components. Each of these testing phases has a corresponding phase, which we talked about. Testing often occurs in parallel with the development. And actually, if you're working on a very big project, that's actually sort of key. In order to get your blue widget product out to market or completed on time, you almost have to do your testing in parallel with your design, right? So there will be phases. Here's phase 1 of my design. It doesn't do everything. It does some of it, but it doesn't do all of it. So test what I'm giving you. Don't test those functionality that I haven't done, because I already know it doesn't do that. But you release it in phase 1, phase 2, phase 3, right? Testing is a way to check that the actual behavior or component of the system matches the expected behavior. When I flip the switch, that should happen, not those 12 other things that occur. In order to test the system, you must have a thorough knowledge of the system's expected behavior, right? So really, the testing people are some of the smartest people when it comes to what the thing should do, because they've spent so much time with it trying to make sure that it works correctly. Should you just plug it in and throw a switch? Sure. Do I have to go back to this? Perhaps not. You might want to take a little bit more of a careful approach and make sure, for example, in that case, that your power system works out correctly for you before you do it. You could have a real setback. And when you create tests, which you will be creating tests, you want to make sure that the tests test as much of the system as possible. You can write good tests and you can write bad tests. A bad test just tests a little something that's done all the time. What you want to do with a good test is test a chunk of functionality and make sure that it actually works. All right, so let's take a look here. So types of testing, and there are many, many different types of testing. The world basically breaks up into 2 types of testing. One is called white box testing, and one's called black box testing. So my question to you is, what's black box testing? What was that?
You don't know what's inside.
You don't know what's inside. It's a mystery. A wonderful mystery for you to discover, right? So if you don't know what's inside, how can you test it? Okay, so that's all you have to work with, right? So in this, what is this? This is a transistor amplifier. How many inputs and outputs do we have to work with here?
1 input, 2 inputs, 1 output.
Well, yeah. So there's you can count it a couple different ways. We sort of have 1 input. We've got 2 sort of control signals, and then we've got sort of 1 output. Exactly. That's all we have to work with, right? Do we know anything about what's inside it if we're doing black box testing?
No.
Not a clue, right? Is this sort of like what you guys did in your first engineering lab? This is sort of classic stuff. Here's an oscilloscope. Tell me what the circuit looks like. Did they do that with you? Yeah. I've got some really bad memories of that. That just was not fun for me at all. But yeah, effectively, that's what black box testing is. It's pretty powerful stuff. Typically done by changing the inputs and watching the outputs. So if that's black box testing, what's white box testing?
You know what's inside?
You know what's inside. So you know all about these resistors and capacitors and stuff like that. So if you know what's inside, what do? You cheat, right? Absolutely. So in this particular one, we've got a couple control points, VB, VC, and VE, right? We should be able to dial those up and dial those down and make sure that the circuit does what it's supposed to do, correct? Excellent. Design is said to be testable when the failure of a component or a subsystem can be quickly located. Makes it easier to design, manufacture, and service in the field. You can increase the reliability of your design by increasing two things. Its controllability and its observability. That sounds sort of interesting. Controllability is the ability to set any node of the system to a prescribed value, such as VB right there. Observability is the ability to observe any node in the system, so be able to measure these at any particular point in time. Black box testing, your controllability and your observability are pretty low. White box, they're both actually a little bit higher. So that's all good stuff there. Stubs. This sounds pretty good. All right, so what are stubs? So stubs are valuable aids in testing. They're commonly used in software testing. Software testing, they're used all the time. So you guys do software testing? Any software testing? What would a stub in software testing be? I don't know. It'd be something where you would have any anything going on in it. Basically, you call it and come back, right? Not too much going on. It's fake code, basically. It's just a stub. It's just stuck in there. So if you call subroutine, it goes, it comes right back. Really, probably doesn't do very much at all. Same thing in testing of an electrical device here. So in this particular situation, this is our little amplifier circuit right here. So what we have here is we've got a function generator. We have the ability to dial it up and dial it down, so we can go through a whole range of them. And over here we have a variable resistor, so we can change that and be able to test things there. Stub is a device that's used to simulate a subcomponent of the system. Typically they're used to simulate the inputs and monitor the outputs of the circuit, also called the unit under test. And they're also used to ensure that the subsystem operates correctly before connecting it to the rest of the system. And I can flick back to the burned out component, but you get the gist of it, right? If you can hook it up to a stub, run through a series of values, make sure it doesn't burn out, you can protect the rest of the system before you hook them all together. Just saying, sounds like sort of a good thing to do, right? How to include stubs should be part of your overall design. So as you're working through your design, you should be thinking about how you can break off parts of it, stub in, test it out, make sure that it works out, and go from there. This is also sometimes called a test harness. Test case property. So if you were going to write a test case or create a test case, what characteristics should it have? I have no idea. You're writing a test case. You guys have done this before. I mean, you may not have called it a test case, right? But you created a design. It had some problems, let's just say. Okay? So then you have to do some testing. Now, have you done anything that was like a longer-term project? A little bit, yeah, so you had to sort of come back, you had to test it over and over again. So if you create a test case for it, let's see, let's think about it. Accurate. Right. The test case that isn't accurate isn't really going to do you a lot of good, right? You get bad numbers from it. It should test what it's supposed to and exercise an area of interest. So do you create just one test case to test a design?
No.
Why not?
Because there's different scenarios.
Different scenarios. Well, why don't you just clump them all into one?
If you can simulate
And
them.
it can come back with a thumbs up or a thumbs down, right? Woo, it works last week. I guess the problem is, if you're anticipating finding problems, right?
That's why you use stuff like variable resistor.
Ah, exactly, right. So you can have a whole series of different values. And in fact, that variable resistor might work for a whole range of values and then fall over when you hit a particular value, right? And you're interested in that particular fall over value. So if you have a whole series of different test cases, what you'll be able to do is divide the world up into two groups, right? Test cases that work perfectly, woohoo, ignore them. Test cases that fail horribly. If they fail horribly, then you've got an issue, and that's where you really need to spend your time. All right. Accurate is good. Economical. The test should be able to be performed in a minimum number of steps. As you get into larger and more complicated systems, what you'll discover is you can write tests that take forever to run. Right? I need to go through 10,000 cycles to determine if this problem shows up. I need 12 hours of burn-in time before I can tell you whether or not that's going to happen. Okay, that's fine, but when you have one test out of 1,000 tests and you have to run all the tests before you can say the next version of your product is good, that's going to kill you right there. So really you want each one of your tests to run as quickly as possible. It's not always possible. You know, some things are time dependent. But you really want to make sure that all of your tests take up as little time and as few resources as possible, because you're going to have a truckload of tests to run. So really, the art of creating good tests is a whole separate art. It's almost like the design art, right? Anybody can write a test case. I mean, it's not that big of a deal. Only some people can write good test cases, and test cases that work well with the other ones. Limited in complexity. Test cases should consist of a moderate number of tests or steps to an individual test. If you were really clever right now, you'd put your hand up and you'd say, Dr. Anderson, that 10 to 15 number reminds me of what we talked about when we talked about flowcharts. Because we said that flowcharts should really only have probably 10 to 15 blocks to them, because otherwise they become sort of too complex for people to figure out what's going on. Same thing with test cases. So in other words, when you're building a test case, stop after you've gone through about 10 to 15 steps and said, listen, that's it for this test case. Okay, I'm all done with it. I should start creating another test case. Repeatable. So the test should be able to be performed and repeated by another person. The other day, by the way, a bunch of scientists over in Europe said, hey, we ran into a little problem. We seem to be able to send light from point A to point B faster than the speed of light. You remember that? That's sort of like a oops type of deal.
Send light faster than the speed of light.
That's what they said. They said, sorry? Okay, that's fine. It's all good. Anyway, so what did they do? They said, look, this is what we did. And what did they ask other scientists to do?
Verify.
To verify. And how would they verify? Basically repeat it. Were they able to repeat it? I don't think they were. I think the gist of it, actually, if I recall the way that story turned out, there was a very smart scientist who said, turns out the geosynchronous synchronizing of the satellites that they've used for their very, very, very accurate time source, it turns out that they put a little bit of skew into the system, and that little skew was just enough to throw things off. But the gist of it is whatever test you come up with needs to be able to be repeatable by somebody else. So if you run into a problem and go ask for help, somebody else should be able to run your test, go up, I see what the problem is, and go from there. All right, what else we got? Has to be appropriate. Okay, complexity of tests should be such that it can be performed by other people who are doing it. If you make it super complex, this is the best test ever because it does all this funky stuff. Yeah, job security. Yeah, that never seems to work out. Engineers, lots of engineers think that, but you know, it turns out we can get rid of you and get somebody to rewrite your tests. Okay, it's not going to cost us that much. All right, traceable. Test should verify a specific requirement. So each one of those requirements that you had in your requirement specification, you should have a test case or set of test case for. If I'm going to give you a blue widget and I'm going to sell it to you for $1 million because it does 5 things, it had better darn well do those 5 things. You better have some test cases that proves that it does those 5 things. This is a subtle one. Self-cleaning. The cool thing about self-cleaning is when you get done running a test case, your system is in some state. Armed, potentially, right? What you want to do is you want to return the system to whatever your base state is, because then you're going to run your next test case. Take it from the voice of experience. If you run that second test case when the system's still in whatever weird state you had it at the end of the last one, everything's going to be screwed up. So at the end of each one of your test cases, you want to reset the system. That doesn't mean flick the power switch. You want to reset the system back to some common understood state. Question?
So in testing things that, like you're trying to find the limitations of the device, and once they reach that, the device will no longer be usable, would self-cleaning be having multiple identical devices?
So you bring up an interesting question. So if I'm testing a device and I want to test its boundary conditions, right? Ideally, I want, the real question that I'm testing is, can it operate at this level? I'm not really trying to break it necessarily.
But you're trying to find the point at which it's no longer operational.
I'm not, though. It's a good question. If I'm a scientist, yes, I am. If I'm an engineer, I'm not. As an engineer, I want to verify that it operates to this level. I truly don't care if it doesn't operate beyond that level.
Well, what about like car crash tests? Like you want to find out to what extent.
That's true. Now, they're not actually producing a product, but let's talk about car crash tests, because that's a good point. So in a car crash test, if you were running a car crash test, what would you do? You would take a perfectly wonderful automobile, right? And you would instrument it to no end, right? You'd put speed sensors, impact sensors, monitors, you put video
But
cameras.
like once the car's crashed, you can't restore it to its original state.
You absolutely cannot. But the starting state for the crash is basically what you want the next crash to start at, correct?
Yeah, that's
That
what
would be quarter mile down the road is 0 acceleration velocity when you start the test. So that one, you're destroying what you're actually testing, correct? So obviously you won't be restoring it. But in that particular situation, every single car crash, you'd want to start from pretty much exactly the same
Yeah,
state.
you would have multiple of the same cars to test.
That is exactly right. Now, if you were testing a camera, for example, right? A camera,
Yeah.
right? Let's say you want to test that it can take a picture, right? So I turn it on, I point it at something, hopefully it auto-focuses, I snap the picture, the image goes into the sensor, gets recorded on some sort of storage media, and gets stored in probably some sort of file system, correct? Now I want to return that camera to some known state. Remember, most cameras have 6,000 modes, easy mode, professional mode. I want to return it to a very specific state, click, and then I'd want to run my second test. And the second test might be test the video movie taking ability. But I know where I'm starting from, standard state, easy mode. I'd go to the video movie taking, I'd do a test there, and then I would go back and put it into the easy mode, click, and I'd be done, right? So that's what I mean by going self-cleaning. You always start from the same state. Car crash, you're destroying the thing that you're testing, so it's a little bit of an odd situation, but no matter what, in a car crash situation, you will always start those tests from the same spot, right? I'm a quarter mile away from the brick wall, I have a 0 velocity, you know, potentially the temperature of the room is always pretty much the same, just because I'm eliminating a whole bunch of variables by doing it.
I mean, when they test, like a lot of power electronics, say you test it until, like, you would try to test it for, like, certain conditions like heat, or like when something would overheat, and in that case, you would probably find out at what point the device is destroyed.
It's a separate test case, though.
You see, you're talking almost about like underwriter laboratories types of testing. The trick is that if I'm producing a product, I'm going to tell you that my product works under a set of conditions. And when I'm doing my test cases for it, I'm going to prove that it works under those sets of test conditions. What you're talking about is pushing that and trying to figure out under what set of conditions it doesn't work. In all honesty, for my products, I don't really care about what conditions it doesn't work under, because I grant you there are some. What I really care about is that when I'm telling my customer, internal or external, doesn't matter, it works up to 100 degrees Fahrenheit. I will test up to 100 degrees Fahrenheit. I will make sure that it works. I will not test up to 101 degrees Fahrenheit because I don't care. I'm not telling anybody that it could fall over at 101. Not a problem whatsoever, because I'm just telling you that it works up to 100. And it's not worth it to me to spend the time to go, oh, look, 110 that it has problems at. Doesn't matter, because I'm only promising you that it works to 100.
What happens a lot to us is marketing comes to us and asks, what range does it work in? And then we have to test.
Exactly. And generally what happens is you do have somebody who does a test that discovers it falls over at 110. And then what you do is you get the legal guys involved and you back off like 5 degrees from that, right? You don't say it operates up to 110, you say it operates up to 105 and click. That's pretty much what's out. Does that answer your question?
I think so.
Okay. All right. Debugging. Know your bugs, as we like to say. So you guys have all encountered bugs. Basically, when you design something or build something and it doesn't work, we say lots of things, not all of it repeatable in a typical engineering class, but let's call them bugs. They are flaws in your design. It causes your design to operate in a way that you had not anticipated, all right? Okay, it's going to take an application of your debugging skills to fix this, to eradicate your fantastic design from the bugs that you have. There's actually 2 categories of bugs, and this isn't actually what they look like, but these are actually bed bugs, which is extraordinarily gross if you think about it. But we call them, there's Bohr bugs and Heisenbugs. And we call them that because they're actually easy to remember. So a Bohr bug is based on the Bohr model of the atom. And if you'll recall, well, maybe back to high school, I'm not quite sure when the last time you bumped into it. But Bohr said there was electrons had a distinct place in space. You could point to them when they were there, which is fantastic. Now, those are the kind of bugs where if you do this, your design does this, and it shouldn't. So every time you do this, your design is going to do this. And you go, well, that's a flaw. So I can make changes, and then I can do this, and if it stops doing that, then I have fixed my problem. Yay, those are great. We love those types of errors. Because that's, find it, fix it, it's good to go. Life is grand. Unfortunately, those aren't the only bugs out there. The other ones are Heisenbugs. So what is the Heisenberg uncertainty principle? What is that?
You know its location, but you know its velocity.
It has to do with-
You can't know both.
You can't, exactly. So you can't know both things, right? If you know where it is, you don't know how fast it's going or something like that. And if you know how fast it's going, you don't know. And what does the picture look like?
It's a cloud.
It's a cloud, right? It's somewhere over there type of deal. Yeah, so these are the problems that more often than not show up. Okay, so what this is I did this and it did this wrong thing. Darn, I went back and did this thing again, but it didn't do the wrong thing. It only does the wrong thing occasionally, under a different sets of conditions. It's not a real clear A causes B type of thing. It's I'm doing something, it's been on for half an hour, and it does this. So it's a whole series of things along those lines. Great. So when you bump into either one of these, what do you need to do? Really 4 steps. The very first thing is you have to observe it, right? You actually have to see the problem happening. If you don't see it, you're not going to be able to fix it. Secondly, you're going to have to hypothesize. You need to come up with a guess. Okay, I mean, ultimately, that's what all this debugging stuff is. So you taking a guess. Okay, I see that happening. What could possibly be causing that? Then you have to do some experiments. This is where the hours come in, right? Where you spend a ton of time working on this stuff. And then, of course, you repeat. And this is a very iterative process. You do it over and over again until you fix the problem. The really good testing engineers are the ones who are able to make good guesses. Their hypotheses are pretty close to whatever the problem is. That's where that voice of experience comes in. It says, hey, look, I think I've seen this before. Why don't we go ahead and give this a shot?
4 bugs usually turn into Heisenbugs when you show the developer.
that is unfortunately true. These can migrate between each other depending on. In the world of software development, this is when you get like memory corruptions, right? Everything's going fine until the memory gets screwed up, and then all of a sudden the system just starts going wonky on you. And those Stack Overflow, exactly. Those can be tricky to do. In the world of electrical circuits, if you have a floating ground, this will kill you every time, right? It's going to have some bizarre and strange behaviors, and it's just not going to repeat itself. All right, so let's talk about unit testing. Unit testing, integration testing, validation, and system testing are the whole family of testing. So unit test is a test of functionality of the system in isolation. So we're going to take a very, very small component of your design, as small as we can possibly make it, and we're going to test it. The unit test consists of a set of test cases used to establish the subsystem, and we perform a single unit of functionality of testing on it. The goal is to write test cases with the goal of uncovering undiscovered defects, because you want to find out what's broken at the smallest unit before you start moving up the stack, so to speak. Unit testing is easier when you've designed your units that are highly cohesive and loosely coupled. We talked about that the other day. What does it mean to be highly cohesive?
Work all together?
Good question. No. It does one set of functionality. So I have a module that does one thing and does it very well. What does cohesive mean? Repeat your answer.
That's it. It works well as a unit.
Exactly right. So it works well. Basically, when it's cohesive, it means you sort of minimize the links to the other units, right? You want everything to hook into everything else, but if it's like an octopus hooking into 1,000 other units and it's broken, you're going to have trouble trying to figure out where the actual break occurred. Okay? Best time to write your unit test cases is when you're actually designing the unit. We talked about this, right? So design and testing go hand in hand. Each path through the system represents a potential test case, and what we call test coverage. Ooh, vocabulary term, test coverage means how much of the functionality of your design is covered by your test cases. So if your design does 4 functions, and you have test cases that cover 3 of those, then obviously you're about 75% coverage, right? Your goal, of course, is 100% coverage. I have test cases that fully test my design, test all the functionality. If I run the test cases, and all the test cases work out, then I'm extraordinarily confident that my design works correctly, and I can sell it or pass it on or do whatever. Matrix test. Okay. So this is sort of the grind, the plug and chug approach to it. So this matrix tests are best suited when you have to do some testing, but the only thing that you're doing is changing the values. I have a whole series of values that I want to run through. So in our original, transistor amplifier, we had basically 2 values, right? We had the input value that we could change, and we also had the VCC value. Very simple here. So this one is analog to digital converter functionality tester. We have a VT value, and we've got a clock value. You can start at 0 and 10 kilohertz. Here's our expected output, poof. Then we just pop it up, right? So we're up to 2 volts, up to 5 volts, hang out at 5 volts and vary the clock value. Then we go up to 2 volts there, change the clock value again. You can produce massive tables of different values. You get the gist of what's going on here. So when you have a matrix test, You produce all the input and output values, you go ahead and you do your tests, and eventually you get a very clear, hopefully, image of what's going on. When you're working on your capstone tests, this might be something you want to consider here. Okay? It'll have different systems, different components and stuff like that. But basically creating a matrix and saying, look, I want to make sure that I test all the things that I have to test. This is going to be a good way to do it. However, of course, it's not the only way. Automated script tests, this is good. It's not perfect, but it is pretty good. Testing can be a very manual process. If you can automate it, then that is fantastic. It makes your life a lot better. An automated test script is a sequence of commands that are given to a system that's under test, of course. The outputs for each input are then verified against pre-specified values. There is some extraordinarily expensive hardware and software sold by companies that do a very good job of automated tests. An example that you guys have encountered pretty much every day is a memory self-test that a computer does. Remember, it writes a value, a series of known values to memory, and then it reads those values back and confirms that it got back what it thinks it wrote to it. So that's a very simple automated test script that we see every single day. What else we got here? Oh, step-by-step tests. Remember our candy machine example when we were doing our state machine? Same type of deal. We can go over here. We can say, look, I want to test to make sure that the candy machine is working correctly. So once again, we're going to make a finite state machine path test. So what do we have here? We're going to say, look, I'm going to put in a nickel. The internal state should go to 5 cents. I'm going to put in a dime. We should be up to 15. We're going to wait. So if I don't do anything, with a little luck, the machine's value isn't going to change, right? Go ahead and put another nickel in. We're up to 20. Put a dime in. Then it goes to 25. Although there's a problem there, isn't there? What should happen when I put that final dime in? I think you should go up to 30, right? Remember, this was the downfall. Well, from a user point of view, this is the downfall of this particular candy machine. Thank you for the extra money. I'm not going to give you any change, right? Nothing happens. This is basically when the candy's being kicked out and state goes back to 0. Poof, right? So once again, you can see that this is a legit set of test cases here. Okay? What we're doing here is it's a step-by-step test case. It's a prescription for generating the test and checking the results. The descriptions are most effective when the test consists of a complex sequence of steps. Because these are all taken together are really the test, right? This isn't a test. This isn't a test. The whole thing together to verify that we can actually take 25 cents and crank out a piece of candy, that's the test. The test template for the step-by-step test has all the information contained in the matrix test template. So this is very similar to the matrix test template, but it's just that we're sticking it all together and then calling all of this a single test. Okay? The world is made up of more complex things. Integration testing. So remember, we've done our unit testing. We've confirmed that the low level, the potato cellar, so to speak, of our design works correctly. Woohoo! But that's not good enough, is it? What we need to do now is make sure that all the individual components work together to provide the functionality that people are looking for. So we move on to something called integration testing. Remember, at whatever company you end up going to work for, there will be a department called integration testing. And this is exactly what they do. So when they're putting together their integration testing test cases, they're going to have to ask themselves some questions. Here's 4 of them. So what are the different paths of execution through the system? So once again, if I'm creating my Blu-ray DVD player, woohoo! There's a bunch of things I can do with it, right? I can turn it on and not have a disc in it. It's got to do something, right? I can turn it on, I can have potentially a non-Blu-ray disc in there. Should I play it? Should I not? If I can have a Blu-ray disc in it, that'd be fine. Maybe I'm trying to watch Netflix on it. There's all sorts of different paths I can be taking here. You best be having test cases for each one of those paths at the integration level. Are all modules being exercised at least once during the integration testing? This is a trick, okay? And this comes down to when you're writing your test cases. When you write your test cases, you have to make sure that you exercise all the functionality there. And that means that you almost have to really be doing white box testing here. You have to understand what the system can do, and you have to write the test cases to make sure you hit each one of those spots. It's like going from Florida to New York and saying, I want to hit each state on the way. You could skip some states if you didn't want to hit them. But what we're trying to do is test to make sure we make each one of them. So you have to pick your path correctly. You have to make sure that all the interface signals have been tested. You know, that's a huge one, right? You're going to have to trigger each one of the different input signals there, because if you don't, guess what? That's what your very first user is going to do. You have to make sure that all your interface modes have been executed, which ties into that. And then finally, does the system possess information at the required rate meet timing requirements? Timing will be your biggest nemesis as you go forward. Signals don't show up in time, signals show up too late, signals show up too quickly. What happens is when you don't have the right inputs at the right time, all of a sudden you make bad decisions. Okay? After the units of system have been created and tested, then they must be integrated into larger subcomponents, and the test cases for integration testing are traceable to the high-level design, and the test cases are written based on the characteristics of the design architecture. So at this point in time, we should be able to start tracing back to the engineering requirements, which that also means we should be able to get back to the customer requirements. Acceptance testing, we're just about at the top of the pyramid here. Getting exciting. All right, so when we're doing acceptance testing, this is really the top level, the highest level of testing. No longer are we really concerned about what's inside of the device that we've created. Rather, we're talking really about how the thing works. Because acceptance testing is often called user acceptance testing. So I'm the user. Give me my Blu-ray DVD player, and I will tell you whether or not it works. A couple different things. System requirements and system specification go together. You create a test acceptance plan, and that's actually what gets executed. These are very readable. Okay? There's no engineering jargon in these. Press this button. You should see this. Do this. You should see this happen. An acceptance test plan is a formal document stipulating the conditions under which the customer will accept what you have designed for them. It verifies the system meets the requirements specification. Ideally, the acceptance plan is developed with the engineering requirements and should be traceable to them, and it should also identify the scope of the test. How much will be tested, the testing approach, and to which level the acceptance test will be taken to. How far down are you going to go with this? Last slide. You ready for this? Why do testing?
Make sure it works.
Well, that sounds like a good one. Any other thoughts?
Verifiable.
Safety. I like that. That's good.
So
Environment.
you don't get sued and go to jail.
Okay, I'll go with that. That gets into the other stuff. You know, it
Think about yourself there, Ken.
Costs less money.
costs less money if you can find it early and fix it. That's right. How about employment for electrical engineers? I mean, I don't know if you don't care about having a job, don't sweat it. But a lot of engineers are employed doing testing, right? It's a complex technical task. You can't just get somebody to come off the street and write test cases for whatever device is being created. It really takes a great deal of understanding of what's going on. And guess what, guys? You're being trained and educated to do that. Well, let's see if I can come up with some good reasons. First one, reduces number of bugs. All right, I think we said that. That's fantastic. Tests are good documentation. You know, that's actually an interesting thing. So lots of things that we use today were designed in the 80s. Okay, the people who designed them have moved on, or died, or who knows what happened. They're gone. So how the thing works is going to be tricky to determine. Now you can look at like user documentation, but that's always sort of iffy, right? There's a big gap between the engineer and user documentation and the pretty little binder and stuff like that. You know, the test cases though, test cases never lie. Right? If you can run the test case and it verifies, and if you look at the documentation that goes into the actual test case, I'm going to do this because I want to see this, it's an excellent documentation for the design. Tests reduce the cost of change because we caught it early. Tests improve the design. You know, that's actually one of the key reasons why you want to do testing as you're doing your design, because you may discover that your design sucks early on. If you're doing your testing, first off, it's not working. Okay, that's the first clue. But secondly, what you might be discovering is that it's really hard to test. Now, if it's really hard to test, then maybe there's something wrong with your design. You should go back and take a closer look at it. Tests allow you to refactor. Basically allow you, once you get it working, hey, look, I've designed it, it's working, everything's good, you can then simplify it, okay? And then you can run your test again, and hopefully you're still getting a good answer. Test constrained features, you're able to limit the functionality that goes in, because remember, there's something called scope creep, where people go, oh, hey, that's great, you did that. Could you do this? Could you do this? Could you add just this one extra feature in? Say, hey, listen, it's not inside the test cases. Test cases defend against other designers. Hey, you know, I say how you're doing it there, but you could do it better this way. Say, listen, I've done it, I've tested it, it works, let's move on. Testing is fun. Oh, come on. You know it's got to be fun, right? test something and it works perfectly, what a great feeling that is. Or you test something, you find that it doesn't work, and then you fix it. What a sense of accomplishment when you go home that evening. Okay, testing forces you to slow down and think. Sometimes we run at 80 miles an hour if we're wide open and stuff like that. We're cranking design left and right, and that's fantastic. But if it's junk, then we really truly do need to slow down and take a moment and make sure that we're producing good design. And if we're doing some testing along the way, and it's telling us that we're producing junk, then that's our heads up. And finally, testing will make your development go a lot faster. If you test it, you verify it, you've got great unit tests, all your individual low-level components work. When you start assembling it into a complete system, rock and roll, you're taken care of. Everything will work the way it's supposed to. Capstone! Should we talk about your capstone? Alright, so let's see, Tuesday 11:15, which is next Tuesday, right? You got something to do, right? What is it? Oh, hey, how's it going, guys? Has anybody met with a member of the electrical engineering faculty to talk about your capstone? We've got at least one person here. Two. How's it going? So have we had 1 meeting, 2 meetings, 3 meetings, or 1?
Already had
2? 2? Anybody do 1? Okay. Anybody do 3 yet? Okay, well that's fine. So how'd that meeting go? Thumbs up, thumbs down, thumbs middle? Were they excited? They say this is the best capstone I've ever seen.
Yes.
One was.
Nobody's ever. There are a couple different ways to interpret that, but that's okay. Did they seem interested in your capstone? Have you decided this is the person you want to work with?
Yes.
Sometimes that works, okay? But you still have to meet with 2 more. Because, it's like dating. Wow, you're the best person ever. Oh, wait, there's somebody else. Ooh, right?
What if he's my high school sweetheart?
Well, so be it. That's fine. What will happen is you'll meet with 2 more, and that will confirm that he is the right one for you. Somewhat disturbingly, but that's fine. Okay? So you have a little bit of time, because today's not next Tuesday, but 1 week from now, I want you to have met with 3. I want you to have filled out this table, guys. Right? And it's all, you remember, you're doing the interview. And remember what my psychic prediction is for you. You're going to meet with 1 faculty member who thinks your idea sucks. Who may tell you that, or may just sort of hint around the edges. That's not quite as sucky as some of the other ideas, I think, right? You're going to meet with 1 faculty member who seems to be bored. Well, okay, that's a lovely idea, right? Whatever, and just not that excited. And hopefully you'll meet with 1 faculty member who actually seems to be sort of interested in what you're doing. And thinks that you've got a good idea, you need to maybe change a few things, but there's some merit to what you're doing. That's my psychic prediction for what's going to happen. You'll have to come back and tell us how it goes. You may meet with people, all 3 who say that your idea is lousy, or you may meet with 3 that say, that's the best idea ever. We're a month behind the Nobel Prize application, but it's okay, I think we can still get in. All right? So keep at it. You got a week to pull this off, just make sure that you don't try to do it all on the last day. They know that you're coming, so hopefully there won't be any surprise on the faculty parts. You're also working in your ethics essay, right?
Oh yeah.
Because that's due like Thursday, right? In class. You're going to come in, you're going to drop it in, and everything's going to be good to go. I'm excited about that. So here's what the schedule currently looks like, guys. We already did that. We're here on the 8th. On the 10th, your ethics essay is due in class. The following Tuesday, your capstone mentor worksheets are due in class. Okay? There's got to be at least one more thing here. What do we have? Whoops. All right, hey, let's talk about our schedule for the rest of the semester. Once again, just trying to sync up with you, make sure we all know where we're at here. All right, so today, we talked about testing. Ooh.
What?
Ethics panel sessions. Teams 1 through 6, and then teams 7 through 11. I've given you your assignment, right?
Yeah.
I haven't, have I? Well, then I should do that right now. I would like 1 representative from each team to come up.
Yeah, no.
Oh, wait a minute.
Come on, Scott, get something to it. Okay. You failed last time.
Yeah, they made it.
Mr. Samuel,
Yes.
are you going to be my California representative?
Yes.
I have 6 pieces of paper here, Mr. Samo. Would you please select one? Three. Okay. Team Texas. Come on up. Mr. Vaughn, would you please select one of yours? Yes, sir. Team New York. All the good ones are to the left. Up, we got.
Oh, come on, Ed Penabone?
Florida? What do we got from Florida? Mohammed, take one, please. What do you got? XYZ. And finally, Team Illinois.
Interpret it as you will.
Pennsylvania? You can pick any one. Which one is it? Antenna.
Come on, Scott.
Cool, all right. Fantastic. Now I got 6 more teams, don't I?
Yay! Yay! Don't think of it as a competition, it's a healthy debate.
Team Ohio.
Discussion. A sharing of,
What do you got? Space.
Sharing of different opinions.
yes.
Team Michigan.
Standing right now? Bro.
Yes, me. Team Georgia. Mir? Whichever one you want.
No.
So,
Space show.
Oh, space shows, yes.
Yeah.
Team North Carolina.
Like the challenger thing?
Yes, me. Exciting as much as yes, sir. Team New Jersey.
I can't even say it.
What is it?
I don't know, I can't even say it.
Okay. And Team Virginia. All right. So let's see. Teams California, Texas, New York, Florida, Illinois, and Pennsylvania. I have fantastic news for you. Your ethics assignment is online. Basically what it is, it's a description of a particular ethical situation. What you need to do is you need to go online, you need to find it, you need to read it. I would actually suggest that you have a discussion amongst yourself as a team about sort of how you feel about it. Who's right, who's wrong, what are some of the considerations. On Thursday, I'm going to call the team, such as Team California, to come on up, be in front of the class. I'm going to ask you to describe your ethical situation to the entire class. Okay? We will have a class discussion. We will ask you questions. And because you've spent time studying your problem, you will have rapid-fire good answers for that. We will probe. We will challenge you. We will ask you why you made the decisions that you did. And you will be able to build on the ethical framework that you've developed during the entire semester to come back with solid answers that impress us with your ethical decision making. Now, the other 6 teams, I haven't put it online. I will put your cases online on Thursday. Don't want to give you advantage. Are there any questions about how we're going to do this?
Wait, you said it Thursday, right?
It's my turn to do this.
So on Thursday, in other words, our next class session, we're going to do teams California, Texas, New York, Florida, Illinois, and Pennsylvania. And I will be excited to have all 4 members from each team up here participating in the panel. And I know you'll be excited to be there. So that'll be cool. All right, cool. We got that taken care of. Sorry. Are there any questions about this? Wait, I'm just saying that as sort of a courtesy, not really meaning any questions.
What do we talk about in these panels? Like, how does that work?
Well, it's pretty exciting because you've never done an ethics panel before, have you? But after Thursday or Tuesday of next week, you will be able to say, I have done that before. So read the ethical case study, okay? Then be prepared to describe it to the class, and be prepared to discuss it, because we will hit you with hard-hitting questions like why? Why did you think that? And did you consider this?
So you're not choosing to pick a side.
You can pick a side.
You
You will.
that far if you're not saying, right? Here, the other
It's not
team's
even
here.
saying it's.
Right, okay.
You're not really in competition with the other team. It's you by yourself. Although if the other team says some interesting stuff when they're doing it, we will ask those questions too also. So there's an advantage to going first, and there's an advantage to going second, but you can't do both. What's that? Out in the parking lot. All right! Real quickly, let's make sure we're all on the same page here, because of course your grade hangs in the balance. Okay, so we did testing today. We've got 2 classes with the ethics panel. Fantastic, you'll do a great job with that. We're going to do one more class talking about how you can become a professional engineer. It's magic, there's some powdered bath dust, and we'll do that. After that, we're going to have a class where we review for the final exam. Let us review and remember that we talked about having our final exam when?
29.
I think it's on the 29th, isn't it? Okay, that's cool.
What about everything else on that whole capstone list?
Well, you have the list. You've been working on it, haven't you?
Yeah,
I don't have to hold your hand the whole
Always
whole
3
this.
quarters going.
I'm going to get you this far, okay? And then I'm going to kick you in the butt and send you out the door, okay? All right? The last class, and this might be the most important message to you. The last class contains a team challenge. It has points associated with it that go towards your grade. So I know you're going to be saying, look, I'm all done with my final, I'm all done with the class. And you don't have to show up on that Thursday. If you don't show up on that Thursday, you get 0 for this. And when I'm working out the grades, and I go, oh, look, you were so close to that next grade. Did you show up for that Thursday team challenge? And it says 0. I will think in my heart, you didn't care enough about your grade to show up on that Thursday. So that's cool. I don't care enough to shove you up to the next grade, okay? But that's our good. There's a question in the back.
Yeah, should we bring your dry pasta and marshmallows?
What's that? No! That you could bring it, but it would not help you at all. This is designed to bring all of your engineering skills to a focus and show you just how far you've come this particular semester. Question.
So you mean we're gonna be like chugging gallons of milk and stuff?
I don't want to brag and I don't want to give away anything like that, but it should be very interesting, and you will leave the classroom a changed person. That's my promise. We're done. Get out of here.